Howdy. I'd like to talk today about how we can use graphs to analyze motion. So far, we have used our equations of motion for constant acceleration in order to solve our problems. And those equations are fantastic, but they require constant acceleration in order to work, obviously. What graphs are going to do for us is they're going to allow us to analyze motion in situations where we might not have constant acceleration. Maybe we do, maybe we don't. And so we are going to talk about how we use graphs to analyze motion. The first type of graph that we are interested in is the position graph. And you can always tell when you're looking at a position graph because you can check the axes and see that your vertical axis here is a position variable, x. And if you're not sure, then check the units because the axes should always have their units, and this guy right here has units of meters, and therefore he must be measuring a position. So let's get a graph of position here on the table and see what we're looking at. This is a nice position graph. Now, first thing we want to worry about is how to read the graph. Each point on the graph is going to give me a position at a particular point in time. So for example, I could go to t equals 5 right here and look and see that we have a position of about 5.2. So I could read the graph for individual points and say that the position at t equals 5 is about 5.2 meters. And that's easy enough. If I wanted to get a sense of all of the motion, I can trace along the x-axis, which is the vertical axis here, the one labeled x, the x-axis with my finger, and see that when we are starting, we are at the point 4, x equals 4, and then as time goes on, we go up until we hit the top at t equals 3, and then we go back down until we hit the bottom right at t equals, looks like about 8.5. So what does this mean? Well, motion in the upwards direction on this axis means going forwards, whichever way happens to be forward. And motion downwards means going backwards, whichever way happens to be backwards. And so we can see that all of this portion of the graph here to the left is forward motion because the graph is going up, and all of this motion is backward motion because the graph is going down. I said going up and going down. The official math term for going up is increasing. The official math term for going down is decreasing. We can actually measure how quickly we are going up or down by considering the rate of change, or the slope. So if I take any 2 points in time, and I compute the slope of the segment connecting those 2 points. For example, let's say I go to time t equals 2, and I go to time t equals 7, and I connect the 2 points on the graph with a line then the slope of that line gives me a rate of change. And in fact, we call this line a secant line because it cuts through, the Latin word is sectare, to cut through. and it cuts through from t equals 2 to t equals 7, right here. And so we would say it is on the interval 2 to 7. And the slope of that line can be written in terms of the variables on the axis. It would be the change in the vertical variable, which is x, divided by the change in the horizontal variable, which is t, delta x over delta t. And as soon as I write delta x over delta t, you go, oh, I know what this is in physics. This is the average velocity. So the slope of that secant line computes the average velocity. Let's get a number for that. The rise looks to be about negative 1, 2, 3.5, and the run looks to be 5. And the units are meters on the vertical axis and 5 on the horizontal axis, and that gives me negative 0.7 meters per second, meaning that on average the velocity is negative. On average, the particle is going backwards over that time interval. Let's see. I wanted you to notice that the way that we figured out how to label that slope was purely from the axes. We looked at the horizontal and the vertical axes, and then once we did, we said, oh, look at that, that's a physics quantity. So the slope of the secant line is then going to give us the average velocity. Now, what if I do a tangent line? To do a tangent line, such as right here, at t equals 5, looks like it's t equals 4.5, right there. So the slope of the tangent line, I'll do that in a different color. Is computed in the same way that we did for the secant line, except that to get a tangent line, we are going to let delta t shrink to 0. So the slope of the tangent line is written the limit as delta t goes to 0 of delta x over delta t. And when we do, that gives us the instantaneous velocity at that point. And to get the slope, you simply take 2 points on the line, here and here, and you find the rise over run. Looks like the rise is about negative 2.5, and the run is about positive 2.5. And the units are still meters for the rise, and seconds for the run. So I get about negative 1.0 meters per second as the velocity at the point of tangency. So the velocity would be at the point t equals 4.5, because 4.5 right here is where I drew the tangent line. So this is what we can do with the position graphs. We can read the position off of the position graph. We can determine whether the object is going forward or backwards by determining whether the curve is increasing or decreasing. We can find the average velocity from the slope of a line that cuts through 2 points. And we can find the instantaneous velocity as the slope of the tangent line. We've talked about all of this before, so I'm going to assume that it's fairly familiar to you. If you have any questions, feel free to put them on in Modo. Now, let's take a look at the second type of graph that we can encounter. And that would be a velocity graph. The reason that I know I'm dealing with a velocity graph here is, again, because I look at the axes ahead of time to determine what kind of graph I'm dealing with. And this is velocity versus time. And let's make our velocity graph be like so. Velocity graphs are a little bit harder to read. I can still use the idea of looking up a value. So for example, here at t equals 3, I can go to the graph, and I can see that the velocity at time 2 is equal to positive 3. I'm just going to put a positive sign in there. And I can see that the velocity at time t equals 6 is equal to about negative 3. Oh, I said that wrong, didn't I? I'm really sorry. Okay, let me back up. How to read? So I can still look up and I can see that the velocity at time 3 is equal to positive 2 meters per second. There we go. Now my numbers are agreeing with what I was saying. And I can see that my velocity at time 6 is equal to negative 3 meters per second. I apologize for the confusion there. So I can read the graph just like that. But what I can't do with the graph is I cannot trace the graph with my finger to see if the object is going forward or backwards. Students will often look at this graph right here and then say, oh look, the object is going backwards because the graph is decreasing. That's not how to read the graph. Instead, if you want to determine if the object is moving forwards or backwards, you're going to have to determine if the velocity is positive or negative. And if you take a look at the graph right here, you can see that right up until t is equal to 4, that my velocity is positive for all of these times. And if you doubt that, just read a couple values off of the graph. Velocity of 1 is about positive 3.5. The velocity at time 2 is positive 3. The velocity at time 3 is positive 2, and so on. All of those are positive values. Likewise, the velocity is negative down here for times that are greater than 4. And so part of reading a velocity graph is to determine when or what times the velocity is positive, the velocity is negative, and of course the other possibility is that the velocity is 0. And right here, at t is equal to 4, the velocity is 0. It cuts through the axis. Having determined when the velocity is positive, negative, and 0, we can then interpret that in terms of forwards or backwards or stop. Anytime the velocity is positive, the object is moving forward. Anytime the velocity is negative, the object is moving backward. And anytime the velocity is 0, the object is stopped. So let's review how we read these graphs here. Of course, I can read individual velocities at individual times. But if I want to determine forward or backwards, I need to first go through and identify the slope, the value, the sign of the velocity at the various times. And once I have interpreted the sign of the velocity, then I can tell whether the object is moving forward or backwards or if it is stopped. So for this graph, we would say the velocity is greater than 0 for the interval 0 to 4, which means that the object is moving forward for those times. And we could say that the velocity is less than 0 for times between 4 and looks like 7 is where the graph stops. And that means that the object is moving backward. And then finally, the velocity equals 0 at t is equal to 4 seconds. And that is when the object is stopped. Stopped in the name of physics. Okay. So what about slope then? Is slope at all interesting to us? Let me erase some of my marks here, and we can talk about the slope of the graph. Let's say I take 2 points in the graph, maybe right here at 1, 3.5, and let's take another point maybe down here at 7, negative 4. And I connect those 2 points with a line, And what kind of line is this that cuts through the curve? Yes, it is a secant line. And so now I want to know the meaning of the slope of that secant line. If I want to know the meaning, then I first need to write its slope in terms of the two axes. And the slope is going to be equal to delta V divided by delta T. Vertical rise over horizontal run. But as soon as I write the slope as delta V over delta T, I realize that I have a physics name for delta V over delta T, and that is average acceleration. So the slope of the secant line on the velocity graph computes the average acceleration, which is going to be about negative 4.0 minus 3.5 over 7 minus 1. Notice that I always do final minus initial, that is the one later in time minus the one earlier in time, which gives me negative 7.5 divided by 6, which is, oh, I don't know, is going to be about negative 1.2. What are the units here? We have meters per second in the vertical axis, and we have seconds from the horizontal axis, so that we get meters per second squared as the units here, which are in fact units of acceleration. The sign of the average velocity is going to tell me on average that the velocity was going down or decreasing. That doesn't mean the particle was going backwards. It means that the velocity was decreasing during that time period. What about a slope of a tangent line? Just as we did with our position graph, we're going to say that the tangent line is the same concept as the secant line, except that we are letting delta t go to 0. And when we do, instead of getting an average acceleration, we get an instantaneous acceleration. So, for example, if I go to the point t equals 3, and I put a tangent line right at that point, sometimes you have to play with it a little bit, really tangent right there, then I can compute the slope of that tangent line as rise over run. It looks like my run, or my rise is negative 1, 2, 3, 4, 5 and a half. And my run looks to be 1, 2, 3, 4 and a half. So my acceleration at the time t equals 3 is equal to rise over run, negative 5.5 meters per second over 4.5 seconds, which is going to be somewhere around 1109. It's going to be about 1.3 or so meters per second squared. That indicates that the object is experiencing a negative acceleration at that time. What can I evaluate from that? Well, remembering again that my velocity is positive during these times and negative during those times, I can see that my velocity is currently positive at t equals 3, but the acceleration is negative. And since the velocity at 3 is greater than 0, in fact, it has a value, according to the graph, of positive 2 meters per second. And since the acceleration at 3 is less than 0, is negative 1.3 meters per second squared, that means the object is slowing down. It's going forward, but it is slowing down because the velocity and acceleration have opposite signs. So we can find all of that out from the graph. Well, there's one more trick that velocity graphs have up their sleeves. So I'm going to give myself a new page and make a copy of our velocity graph. me see if I can select just the curve right there. There we go. There's our velocity curve. So, okay. This is our velocity measured in meters per second, time in seconds, like that. And we already determined that our velocity was positive here and negative there. If I consider the area under the curve, that area, let's say this guy right here, that area represents taking the curve and tapering it with a large number of small rectangles. And the height of each rectangle is going to be a velocity at that time. And the width of each rectangle is going to be a small unit in time, delta t. So that in terms of the graph, the area under the curve is equal to the sum of velocity times time for all those times. But if you think about it, the velocity times time gives the change, the approximate change in position during that small time interval delta t. In other words, let's say this delta t is a half a second, which it about is on the scale, and the velocity here is about 5. When I multiply 5 meters per second times the 0.5 seconds for that time interval, v times delta t gives me about 2.5 meters of distance that the object traveled just during this little time interval right here. And if I now repeat that process for each small half-second time interval, where I go to the height on the curve, and I multiply the height, which is velocity, times delta t, then I get the distance traveled for each time interval. When I add them all up, that gives me the total displacement for that time interval. Now that got kind of messy, so let's come back and make it a little bit cleaner. My curve again. And just say it like this, that the area under the curve represents the displacement during that time interval. And we write that area as the sum of velocity times delta t. Now, how do I find the area of such a small shape? Well, I can't very easily. So usually I cheat and I compute the areas of simple shapes such as triangles. And I look and I see that my shape here, it's not exactly a triangle, but it's close enough to a triangle that I can at least get an approximation. And I can say that between 0 and 5, the delta x is equal to the sum of velocity times time. And now here I'm going to approximate that as the area of the triangle, which is 1/2 of the base, 5 seconds, times the height, which is 5 meters per second, or about 12.5 meters. If my area includes any times for which the velocity is negative, such as from here to here, then the displacement during that time period is going to come out as a negative number, because the velocities are below the axis. So the delta x from t equals 5 to t equals 7, again, is going to be written as the sum of velocity times time, which is going to be approximately, using the triangle here, 2 seconds, excuse me, it's a triangle, so 1/2 of base times height, so approximately 2 seconds times the height of -2 meters per second is going to give me approximately -2 meters. if I were to add both of these together, that would give me the displacement from 0 to 5 together with the displacement from 0 to 7. And that is the displacement, let me make sure I said that right. The displacement in red here is for t's from 0 to 5. The displacement in green here is for t's from 5 to 7. And if I add those, then I should get the displacement from 0 to 7. So the displacement on 0 to 7 would be equal to 12.5 plus -2 meters. This is from 0 to 5. This is from 5 to 7. And when I add them together, I get the displacement from 0 to 7. And that gives me 10.5 meters. We will do a lot of this analysis tomorrow when we talk about non-constant acceleration. But for now, let me sum up our methods of analyzing graphs. There are essentially three things that I can do. I can look up values. And I'm going to use the axes, use the vertical axis label to interpret the meaning of that value. So if I'm working with a position graph, when I look up a value on the graph, it's giving me a position. When I'm working with a velocity graph, if I look up a value on that velocity graph, it's giving me a velocity. So part of looking at values on the velocity graph is using the sign of the velocity to determine whether we are going backwards or forwards. If my velocity is positive, then the object is moving forwards. If the velocity is negative, the object is moving backwards. The second thing that I can do is to compute a slope. And again, I will use the vertical label to interpret the meaning of that slope. On this graph, the slope is going to be a delta x over delta t. On the velocity graph, the slope is going to be a delta v over delta t. And then I'm going to interpret the meaning according to the physics. So delta x over delta t is a velocity, delta v over delta t is an acceleration. And then finally, I can compute area. My slopes were written delta x over delta t or delta v over delta t. The area is only meaningful on a velocity graph. And that area can be written as the sum of velocity times time. And when I add up velocity times time, what that gives me is the total displacement for that time interval.